All right, ladies and gentlemen, in this video, we are continuing our discussion about the segment relationships of circles. And so we are going to be first and foremost, and I just realized that I have a typo here. Let's go ahead and put another L in there somewhere. The goal, again, is to use segments of chords, tangents, and secants to find some missing variables within these segments. And today, in this video, we're going to focus on these two success criteria, identifying the definition of tangent and secant segments, and then utilizing a theorem known as the segments of secant theorem to find segment lengths. So let's talk about just some basic definitions. So when we're talking about tangent and secant segments, well, we know what a tangent is. Well, it's at one intersection right there. So there's a segment that is tangent to a circle. That's all that it is. A tangent that is segment to a segment that is tangent to a circle. A secant, remember, we know a secant is the extension, basically, of the chords, almost in a sense, right? So it's a secant that goes all the way through on at least one of the sides. That's what makes it specifically a secant. But what is interesting about a secant segment is it's broken up now into two parts, okay? There's the secant segment, the entire length of the segment is the secant segment, and just the outside part here is called the external segment. And then think about it, what does that make QR? Well, hopefully you realize that QR is just the chord, right? The chord is inside of that circle. So what about these segments of secant's theorem? So in this case, we are discussing only about when two secants intersect. Remember, we talked about this, that this measure of the angle right here, the angle, remember, would equal half of, what was it? Big arc minus little arc. Half of big arc minus the little arc. But now we're going to talk about the relationship between the segments of the secant. As you can see here, the external EA times the entire secant is equal to the other side's external times the entire secant right in there. So outside times entire equals outside times entire. Take a look at an example. In this case, we have 9 as the external, and the goal is to find the value of x. So right now we know that RP times the entire RQ, don't be confused with 11, 9 and 11, so RQ equals RS times S, whoops, I almost made that mistake right there, RT. Well, RP is 9, the entirety of RQ is 20, 9 plus 11, RS is 10, and the entirety of RT is 10 plus X. So we have kind of brought ourselves into an interesting little scenario here. So we have 180 on the left. Distributive property says we have 100 plus 10x. Subtraction gives us 80 equals 10x. And division gives us that x equals 8 in the end. So there is an example of how we can utilize our theorem regarding secants. And it doesn't matter what the scenario is, it's the same thing. External times the entirety times equals external times the entire secant segment.